Hey guys, welcome. So we're going to do things a little differently this time. I'm not going to post a key for you. What I am going to do is do a video tutorial, right? So this video tutorial will cover all of that last page, that skill practice at the end of ChemQuest26, 1 through 10. Now, you do not need to watch the whole thing. I encourage you to watch what you need to watch. So if you're stuck on a question, you can skip or fast forward or rewind however you need to the parts that you feel like you need help with. All right, but this video will cover all of them and likely be sort of longish as a result. All right, so number one, it says to calculate the number of molecules in 210 grams of water. Now, water, as we know, has a formula of H2O. All right. Now, there's a couple things we need to do here. So notice that I posted this little graphic organizer. This is going to be on every single slide just to help us out. All right. So one of the things you guys need to make sure you're getting good at is recognizing how to navigate this guy, right? So in this case, right, it says to calculate the number of molecules. So that means that the molecules, that is my question mark. So that means I want to end up over there at my representative particles. So remember, representative particles, we use that value or that terminology to represent atoms if it's a single element, or molecules if it's a molecular bond, or formula units in the case of an ionic bond, right? Water, of course, being a molecular compound, we use the term molecules. So this is what we're trying to calculate right here, is the number of representative particles. Now, the other part of these things that we need to make sure we understand is what is our known quantity? Where are we starting on this case? So in this particular example, we are given a value 210 grams. So this is where we're starting. So what we're going to have to do is figure out how to go from mass to moles, and from moles to representative particles. Okay? So let's keep that in mind as we go, and hopefully that will help us to navigate. Okay, so right now we know that we have 210 grams of water. So I'm just going to go ahead and write that. 210 grams of H2O. All right. So in order to go from mass right here over to representative particles here, right, I'm going to have to calculate the number of moles first. So notice these arrows take me from mass to moles, but then I can go from moles to representative particles when the time comes. So I'm going to have to do not one calculation, but two. Okay, so I'm going to separate this out into two separate calculations, but I'll also show you how you can do it all in one shot if you want to. All right, so I have 210 grams of water. Now I can multiply that, by a fraction, or excuse me, divide that by a fraction. Okay, so let's take a look at our graphic organizer. So I know my mass. So I'm going to have to divide by the molar mass here in order to calculate the number of moles. So what I need to figure out is what is the molar mass of water. All right, so all I do is I take the mass of hydrogen times 2 plus the mass of one oxygen. So I write it like this, 2 times 1.01 plus, I have one oxygen, so I'm just going to go 16.00. All right. So when I add those up, I start to get 18.02 grams per mole. Okay. So all I'm going to do is I'm going to divide this, right? Because to go from mass to moles, we divided by 18.02 grams per mole. Now, whenever we divide by the same unit, we get to cancel that out. All right, so what that's going to give me, all right, when I run my calculation is, I'm going to go 210 divided by 18.02. I'm going to get 11.65 moles of water. All right, so what I've just done, by dividing by our molar mass, which was 18.02, mass divided by molar mass is moles. So now I know my number of moles. So my next step is going from moles down here to representative particles. In order to do that, I'm going to multiply by Avogadro's number, 6.02 times 10 to the 23rd particles per mole. So I'm just going to go 11.65 moles of H2O times 6.02 times 10 to the 23rd molecules per mole, per 1 mole. All right? So that's going to cancel out my moles, and that's going to give me a final value of, if I round with sig figs, because 210 only has 2 sig figs, I'm just going to go 7.0 times 10 to the 24th molecules of H2O. Okay? Now, if I wanted to do this in a single step calculation, not a single step, but all at once, instead of splitting it up into kind of like a and a B, right? I can write it all out using the factor label method or the dimensional analysis method. And I could just write it like this: 210 grams H2O times 1 mole H2O per 18.02 grams. Cancel my grams, times 6.02 times 10 to the 23rd molecules per mole. Cancel the moles, and I would still get our same answer up there. Okay? So I would encourage you guys, especially those of you who are going on to maybe taking some AP chemistry or AP physics sometime, to practice doing multiple step calculations like this. But maybe for now, start with this. All right, let's move on. Number 2. So if I have 6.25 times 10 to the 24th molecules. All right, so this is my known quantity. I know that number, right? Which means I am going to start here at representative particles. It tells me how many molecules I have. Okay? What I'm eventually going to try to figure out is my mass. Right? It says how many grams do you have? Mass. Grams is a mass value. Right? So essentially, I'm just going to work backwards from representative particles, backwards from the last question. Instead of going from mass to representative particles, going from representative particles back to mass. Okay? Either way, I'm going to have to get into that intermediate value of moles in order to get things going. All right? So, we have sulfur tetrafluoride, which is going to be SF4. Remember that prefix tetra means 4. So that's the formula of what I'm using, and I'm going to need to know that, right, eventually to get that molar mass value. Okay? So, known quantity, 6.25 times 10 to the 24th molecules of SF4. Alright? So, I need to figure out how many moles that is, because I need to get that mole value before I can get to the mass, which is in grams. So in order to go from representative particles to moles, I'm going to divide by Avogadro's number. Okay? So all I can do is, divide it by 6.02 times 10 to the 23rd. Oops, excuse me. And it just made a mess. So let's try that again. 6.02 times 10 to the 23rd molecules per mole, dividing molecules by molecules, so that's going to give me, let's see, that will give me 10.38 moles of SF4. Okay, so now I am here in moles. Now, next step, I want my answer in grams. All right, so I need to get up to mass. So in this case, go from moles to mass. I will multiply by the molar mass of SF4, right? So first thing we got to do, we got to figure out the molar mass of SF4. We have 1 sulfur, so it's going to be 32.07 plus, because I have 4 fluoride ions there, I'm going to go 4 times 19.00, and that's going to give me a value of 108.07 grams per mole, right? So in this case, I know that I have 10.38 moles of SF4. 1 mole of SF4 is 108.07, right? So I'm just going to take my number of moles, multiply it by the molar mass. So I have 10.38 moles of SF4 times 108.07 grams per mole. And that's going to give me a grand total of 1,120 grams SF4, or you could do 1.12 times 10 to the third grams SF4 if you wanted to use scientific notation on that one. All right, number 3. Okay, this one is a conceptual question. It just says to define what a mole is, right? So this value right here is a magic value, not truly magic, of course, but what it does is a mole is the number of particles. All right, so a mole, right, it says don't give a number, but we know that we have that magic number, 6.02 times 10 to the 23rd. All right, it's the number of particles required for the AMU value, right? So again, this value right here, 32.07, that's the mass of 1 atom. And that the value would be atomic mass units. And this is an exceptionally small unit that we cannot measure on a balance, right? It is a relative scale. So, so things are measured essentially in relative to the carbon atom. So 1 AMU is 1/12 the mass of a carbon-12 atom. All right? Now, but what the mole does is if we take this many particles, 6.02 times 10 to the 23rd, if we take that many of them, what that does is it converts that AMU value to grams. So if I had Avogadro's number of sulfur atoms, it would be 32.07 grams. All right, so this is how many particles are required for the AMU value to equal the gram value. All right, so again, a single atom of sulfur has a mass of 32.07 atomic mass units. Exceptionally small. We could not detect that with even our best balances. Okay, if I have this many particles of sulfur, right, that many atoms of sulfur, I would in fact have 32.07 grams of sulfur. So that's what a mole is. All right, so this one, it says, what is the mass of 3.45 moles of aluminum sulfate? All right, so in this case, we have aluminum, which is a +3 ion, sulfate, which is SO4, and that's a -2, right? So in order to write that formula correctly, it's going to be Al2 parentheses SO4 3. Okay, so we know this value, moles. This is where we are right now. Right? And it's asking for the mass. So this is our question mark. So we only have to do one calculation. So to go from moles to mass, we are going to multiply by the molar mass of aluminum sulfate in this case. So in order to get our aluminum sulfate molar mass, we're going to have to go 2 times 26.98 plus, now our sulfate polyatomic ion has a 3 outside, so that means I'm going to have 3 sulfurs. So 3 times 32.07 plus, now we have 4 oxygens inside the parentheses. We're going to multiply that by the 3, so I'm going to have to go 12, because 4 times 3 is 12, times 16.00, and that's going to give me a value of 342.17 grams per mole, right? So that is my molar mass of aluminum sulfate. Okay, so now I'm going to take 3.45 moles times, because I'm going from moles to mass, which means I multiply 342.17 grams per mole. So let's write that down. Times 342.17 grams per mole. Cross off our moles, and we're going to get a whopping value of 1,180 grams Al2SO4 3, or 1.18 times 10 to the third grams if you wanted to use scientific notation. All right. So it says consider zinc acetate. So zinc is Zn and it's +2. Acetate is a polyatomic ion with C2H3O2, and it's got a -1 charge, so that formula is going to be Zn parentheses C2H3O2 2, right? And we just want to find its formula mass and molar mass. Now, keep in mind, molar mass is going to be the same number, numerical value, as the formula mass. We're just going to have to adjust units. All right, so let's find that formula mass. So we have 1 zinc with a mass of 65.39, excuse me, plus, now I have 2 carbons inside the parentheses, but I'm going to have to multiply that 2 by the 2 outs there, so I'm going to have 4 carbons, plus, parentheses, 3 times 2 is 6, 6 times 1.01, plus 2 times 2 is 4, 4 times 16.00, and that should give me a value of 183.49 AMU if we're talking about the formula mass, because that's just referring to atoms or molecules. Or if I wanted the molar mass, it would just be 183.49 grams. All right. So what this would mean, though, if I just had 1 zinc, 4 carbons, 3 hydrogens, and 4 oxygen atoms, right, the combined mass would be 183.49 atomic mass units. Now, if I multiplied those by 6.02 times 10 to the 23rd, right, this whole unit, I would have 183.49 grams. All right. So, next question. We're going to move a little quicker on these guys. If I have 245 grams, so that means I know my mass. how many moles do I have? So I'm just doing, again, another one-step calculation. I'm going from mass to moles, which means I'm going to divide by the molar mass. Okay? So lithium carbonate, lithium is a +1. Carbonate, that's a -2. So I'm going to need Li2CO3 is going to be my formula. So in order to divide by the molar mass, I need to know what that molar mass is. Right? We'll go 2 times 6.94 plus 1 carbon plus 3 oxygens. All right, and that gives me a whopping molar mass of 73.89 grams per mole. So now that I know my molar mass, right, I can go ahead and plug that number in. So I'm going to take the number of take the mass divided by the molar mass to get moles. So our mass is 245 grams. Li2CO3 divided by 73.84 grams per mole. Cross off the grams. We're going to keep our mole value. So I'm going to erase that really quick. My minor mistake. All right, because we're dividing grams by grams. Okay, and when I do that, I should get 3.32 moles lithium carbonate. Next, number 7. All right, so gold atoms is our question mark. So we want to figure out representative particles here. If I have 400 grams of gold, so I know my mass. So this is going to be a two-stepper. I go from mass to moles, then moles to representative particles. So I'm going from mass to moles, and I divide by molar mass first. Now, it's just gold, so I don't have to figure out the formula mass. I'm just going to take this value. So I'm going to go 400 grams of AU divided by 196.97 grams per mole. All right, I'm going grams divided by grams, so that's going to cancel out. So we should get 2.03 moles of gold. All right, so now I know my mole value. So my next step is going to be going from moles to representative particles, which I'm going to multiply by Avogadro's number. So I'm going to go 2.03 times 10. Whoops, excuse me. Getting ahead of myself. Let's label that 2.03. 2.03 moles of AU times 6.02 times 10 to the 23rd atoms per mole. Cross off our moles, and we should get 1 times 10 to the 24th atoms of gold. Now, you might be wondering why I stopped at the 1 there. I did use sig figs 400. By the way, with sig figs, I wait till my final answer to round to the correct number of sig figs, right? So 400 only has 1 sig fig, so that's why I just did 1 times 10 to the 24th, even though your calculator likely has a bunch of decimal places there for you. All right, moving along. Number 8. It says 68.5 grams of a certain compound contains 5.25 times 10 to the 23rd molecules. Okay, what is the molar mass? This is an interesting question. You guys would have to use some algebra skills on this one, right? So in this case, I know molecules, and I know mass. All right, what I don't know is my molar mass? So that's an interesting conundrum. Okay, so we could do a couple things. We could figure out how many moles we have. All right, and then set up a little algebra expression. That might be the best way to do this one. So let's try that. So I can't figure out the number of moles I have from this value right there because I don't know what that compound is. But because I know how many molecules I have, and I always know how many molecules make a mole, I can figure out my moles from this value. So I'm going to go representative particles here to moles, which means I'm going to divide by Avogadro's number. Okay, and that will tell me how many moles of this mystery compound I have. So I'm just going to go 5.25 times 10 to the 23rd molecules divided by, right, because I'm going from representative particles to moles, which means I divide 6.02 times 10 to the 23rd molecules per mole, right? I'm dividing molecules by molecules, so I can cancel those out. So when I do that, let's see, 5.25 times 10 to the 23rd divided by 6.02 times 10 to the 23rd. I get 0.872 moles. Okay, so I know my mole value here, and I know my mass value. So what I could either multiply 0.872 times x to get 68.5, or I could divide 68.5 by x to get those. So let's just set up an algebra expression. I want to figure out my molar mass, which is my unknown value. So I'm going to go 0.872 moles times x equals 68. Sorry about that. My sloppy writing is getting in the way. 68.5 grams. All right. Now, to solve this one, just divide both sides by 0.872 moles. And so 68.5 divided by 0.872, and I get 78.6, I believe. Grams per mole. Yeah, 78.6 grams per mole. All right, last one. No, two more, excuse me. All right, we have how many grams? That is our question mark, which means our mass is our question mark because grams is the mass. Are there in a container of 2.26 times 10 to the 25th molecules, which means I know representative particles, which means I'm going to have to do two calculations where I go from representative particles to moles to mass. All right, so I'm going to take our 2.26 times 10 to the 25th molecules of dinitrogen and 2-trisulfide S3. And I'm going to divide that by Avogadro's number. I'm going from representative particles to moles. Molecules per mole. All right, and that gives me 37.54 moles of N2S3. All right, so now I know my number of moles is 37.54. All right, so I'm going to go 37.54 moles of N2S3. Right, to go from moles to mass, I'm going to have to multiply by the molar mass, right? And dinitrogen trisulfide would be 2 times 14.01 plus 3 times 32.07. Plug that in my calculator. I should get 124.23. All right, so this is going to be times 124.23 grams per mole. And I should get final value of 4,660 if I round to 3 sig figs grams of N2S3, or 4.66 times 10 to the third grams N2S3 if I wanted to do scientific notation. Uno más. How many molecules? Asking me how many molecules I have, right? So this is going to be my question mark. So this is where I'm going to end up right there at representative particles. I know 325 grams, so I know my mass. So mass to moles, moles to representative particles. All right, so to go from mass to moles, I need to divide by the molar mass. So I got to find my molar mass. 2 times 14.01 plus 5 times 16.00, and that's going to give me 108.02 grams for molar mass. So 325 grams N2O5 divided by 108.02 grams per mole. 325 divided by 108.02. I'm going to get 3.01 moles of N2O5. All right, I'm going to go 3.01 moles N2O5. Right, I know moles, so I'm going to multiply by Avogadro's number to get representative particles. Molecules per mole. I'm going to get a grand value of 1.81 times 10 to the 24th molecules N2O5. I hope this helped. Adios.